In calculus, we use integrals to calculate the area under a curve. But integrals are based on a concept called a Riemann sum. This is where we use rectangles or trapezoids to estimate the area under a curve. In this video, I will show you how to calculate Riemann sums if you're given the equation for a graph under which you would like to estimate the area. This is the third video in a three-part series about Riemann sums. In the first video, I showed you how to calculate Riemann sums if you are given the graph of the function. In the second video, I showed you how to calculate the Riemann sums if you're given a table of values. In the first video, I drew many pictures and diagrams so you could really understand what a Riemann sum is and where these numbers are coming from. In the second video, I continued to draw little diagrams to sort of remind you of where the numbers were coming from and what they really meant. In this video, I'm not going to be drawing those diagrams. So if you have not watched the first video or the second video, you need to go ahead and click this link up here in the corner and watch the first two videos first. Otherwise, this video won't make a lot of sense. I will also put a link to the first and second video in the description. So number 6 says, use a left-sided Riemann sum to estimate the area under the graph of y equals 36 minus x squared on the interval from 0 to 6, using 3 subintervals of equal width. So first of all, let's figure out what these subintervals should be. If we are going from 0 to 6, and we need 3 subintervals of equal width. First of all, from 0 to 6, so that's 6 units. So we know if we divide that evenly 3 ways, each interval is going to have a width of 2 units. So in other words, the first interval will go from 0 to 2, and the second interval will go from 2 to 4, and the third interval will go from 4 to 6. I think the key is to organize your information very carefully. Since we have 3 subintervals, I am going to create 3 columns. So here is a column for my first interval, and here's a column for my second interval, and here is a column for my third interval. So for my method, I'm also going to need 3 rows. The first row is for the intervals. So as I mentioned a moment ago, the first interval will be from 0 to 2, the second interval will be from 2 to 4, and the third interval will go from 4 to 6. When they say use a left-sided Riemann sum, they are referring to the left rectangle Riemann sum. So we are actually calculating the area of 3 rectangles, which we will use to estimate the area under the curve. So the left-sided rectangle would be like this, where the left side is touching the function. So here's an example. I'm just using the middle interval as an example. To calculate the area of this rectangle, you know that the area of a rectangle will always be the base times the height. So what about the base of this rectangle? From 2 to 4, the base has a width of 2. And we know that's the same for each of these intervals. From 0 to 2, the base of that rectangle will be 2. The base of this rectangle will also be 2. But what about the height of the rectangle? Notice that the left side of the rectangle is touching the function. The left side of the rectangle is equal to the value of the function at that number. So the height of the rectangle is going to come from the left side of the interval if it's a left-sided Riemann sum. So for the first interval, it will come from the 0. For the second interval, it will come from the 2. And in the third interval, it will come from the 4. So if it's a left-sided Riemann sum, of course, you will use the left side of each interval. But what am I talking about? How do I calculate the actual height of the rectangle? Well, the height of the rectangle is the value of the function that we're using. Y equals 36 minus x squared. So we can calculate these heights by using y equals 36 minus x squared. For the first interval, we're using the left side, so x is 0. So 36 minus 0 squared. Well, that second term is just 0, so the height of this rectangle will be 36. For the middle interval, 36 minus x squared, we're going to use the 2, the left side of the interval. So this is 36 minus 2 squared. That's 36 minus 4, so that's 32. And then the height of the third rectangle, the left side of the interval is 4, so that's the x value that we will use. So 36 minus 4 squared, that's 36 minus 16, so the height of the third rectangle is 20. So now we can write the Riemann sum by adding the area of each rectangle. So remember, base times height will be the area of a rectangle. So the area of the first rectangle will be 2 times 36. And then the area of the second rectangle will be 2 times 32. And the area of the third rectangle will be 2 times 20. We're just doing base times height 3 times. And that's it. This will be the left-sided Riemann sum. Before we move on, we are supposed to decide if this Riemann sum is an underestimate or an overestimate. We can use the middle interval as an example. We can see that this will be an overestimate because we have captured this part of the area which is not actually underneath the curve. So we have too much area here. This is an overestimate. You don't need to memorize which methods will give you an overestimate and which methods will give you an underestimate, because you can just quickly draw a picture like this one and look at it and see, oh look, this is an overestimate. But what about the justification? If you want to be able to state the reason, you will have to memorize one thing. Here's what I want you to memorize. If you want to decide if it's an overestimate or an underestimate, for the left-right rectangle methods, it's all about whether the function is increasing or decreasing. That's where your justification will come from. For the other two methods, your midpoint rectangle method or your trapezoidal method, it's all about the concavity. Is the function concave up or concave down? Your justification will be based on that. For example, in this case, we were doing the left rectangle method, so it's all about whether the function is increasing or decreasing. This function is decreasing, so we will mention that as our justification. So the picture tells us it's an overestimate, but our justification will be because y equals 36 minus x squared is decreasing. Of course, you have to know your parent functions. When I look at this equation, I know this is the same as y equals negative x squared plus 36. So I know this is an upside down parabola. The plus 36 means that it starts off at a height of 36. So I have this upside down parabola that's going like this. So in an interval from 0 to 6, I'm dealing with a decreasing function. So I can picture all of that based on my knowledge of parent functions. Hang on to that. Number 7 will be very similar to the last problem. This time we are using a right-sided Riemann sum, and this time they are giving us 3 specific subintervals to use. Let's set up a table to organize our information. As before, we will put our intervals on the top row, but we have these three specific intervals. So the first interval will be from 0 to 3, the second interval is from 3 to 4, and the third interval is from 4 to 5. Let's use our interval from 3 to 4 as an example. This is a right-sided Riemann sum. So as we draw our rectangle, focus on the right-hand side of the rectangle. That's where the rectangle will touch the function. Next, we need to calculate the area of this rectangle. So we're going to need the base, and we will need the height. The base of this rectangle, well, it goes from 3 to 4, so the base is 1. And we can imagine the other two. So from 0 to 3, the base of that rectangle will be 3. From 4 to 5, the base of that rectangle will also be 1. So back to our example, the interval from 3 to 4. What's the height of this rectangle? The height of this rectangle will be the value of the function based on the right-hand side. So the right side of this interval is at an x value of 4. So we will use that x value, and we will use the function y equals 2 to the x power to calculate the height of the rectangle. So we're doing y equals 2 to the x power. In this case, the x is 4. So we're doing 2 to the 4th power, which is 16. So the height of the middle rectangle will be 16. You can use your imagination for the first interval and the third interval. For the first interval, the height will be based on the right side of the interval, which will be 3. So the height will be 2 to the 3rd power, which is 8. For the third interval, again, this is a right-sided Riemann sum, so we use the right side of the interval for the calculation. So we will do 2 to the 5th power, and 2 to the 5th power is 32. So that's going to be the height of the rectangle. Now we are ready to set up the Riemann sum, which will simply be the sum of the area of 3 rectangles. Each rectangle will be base times height. So the first rectangle area will be 3 times 8. And then plus the second rectangle, base times height is 1 times 16. And the third area will be 1 times 32. And that's it. This is the Riemann sum based on the right-sided rectangle method. Before we move on, it's time to decide if this Riemann sum is an underestimate or an overestimate. Looking at our little picture, you can already tell this is an overestimate. This rectangle has captured all of this extra area, which is not under the curve. So this will be an overestimate. In AP Calculus, your justification is just as important as your actual answer. So why is this an overestimate? I told you to memorize that for the left and right rectangle methods, it's all about whether the function is increasing or decreasing. This function is increasing. The parent function, y equals 2 to the x power, you know this is exponential. You know this is an increasing function. So your justification will be because y equals 2 to the x power is increasing. Number 8, use midpoint and trapezoidal sums to estimate the area under the graph of y equals 1 plus cosine x on the interval from 0 to 2 pi, using 4 subintervals of equal width. Ooh, we got a trig function. Well, 0 to 2 pi, that sounds real familiar, doesn't it? Let's picture the unit circle. So from 0 to 2 pi, conveniently, it's already divided into 4 equal subintervals. So the first interval will be from 0 to pi over 2, and then the second interval will be from pi over 2 to pi, And then the next interval will go from pi to 3 pi over 2. And the last interval will be from 3 pi over 2 back to 2 pi. Let's start with the midpoint rectangle approximation method. So that's why we have this extra row in here for the midpoint, because that's the x value we will use to calculate the height of each rectangle. So as I mentioned a moment ago, the intervals will be from 0 to pi over 2, and then from pi over 2 to pi, and then from pi to 3 pi over 2, and then from 3 pi over 2 to 2 pi. But now we need the midpoint of each interval. Let's look at a diagram to help us out. So halfway between 0 and pi over 2, of course, this will be pi over 4. Halfway between pi over 2 and pi, well, this is 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4. So all of these red positions represent the midpoints. As in the previous problems, the base of each rectangle will be the width of the interval. Each of these intervals has the same width from 0 to pi over 2. That's a width of pi over 2. And that will be the same for all of these intervals. So these are all the bases. Now for the height. The height is going to be calculated using the value of the function at each midpoint. So the function is y equals 1 plus cosine of x. So maybe I'll use this space down here for a little scratch work as needed, but you should be able to do this in your head. For the first midpoint of pi over 4, we're thinking 1 plus the cosine of pi over 4. Well, the cosine of pi over 4 is radical 2 over 2. So this is just going to be 1 plus radical 2 over 2. What about the cosine of 3 pi over 4? Well, the cosine of pi over 4 is radical 2 over 2. So all of these cosines are going to involve radical 2 over 2. It's just that some of them are positive and some of them are negative. In the second quadrant, where 3 pi over 4 is, cosine is an x value. Cosine will be negative here. So instead of 1 plus radical 2 over 2, it will be 1 minus radical 2 over 2. In the third quadrant, 5 pi over 4, cosine is still negative over here. So again, the value of the function and the height of the rectangle will be 1 minus radical 2 over 2. When we get over to 7 pi over 4, the cosine of 7 pi over 4 is positive radical 2 over 2. So remember, we're doing 1 plus cosine of x. So that's why it's 1 plus radical 2 over 2. Okay, it's time to write the Riemann sum. Remember, we are just adding the area of 4 rectangles. For each rectangle, the area is base times height. So for the first rectangle, that will be pi over 2 times 1 plus radical 2 over 2. For the second rectangle, that'll be pi over 2 times 1 minus radical 2 over 2. For the third rectangle, it'll be pi over 2 times 1 minus radical 2 over 2. And for the fourth rectangle, it will be pi over 2 times 1 plus radical 2 over 2. It's just base times height 4 times. Last but not least, let's do the trapezoidal sum approximation method. So in order to visualize how to organize our information, let's remember a little something about trapezoids. First of all, the formula for the area of a trapezoid is 1/2 base 1 plus base 2 times the height of the trapezoid. But be careful, the trapezoids we are using are sideways from what we're used to. So what would normally be the height of the trapezoid is more like a width of the trapezoid when it's turned on its side. So instead of putting an H here, I'm going to put a W because this is more like the width of each trapezoid. Looking at the formula for the area of a trapezoid, I can see what the rows of my chart need to be. We're going to need a row for base 1 and base 2. So base 1, base 2. And we're going to need a row for the width of each rectangle. So row for W. So how do we find base 1 and base 2? So this is base 1 of the trapezoid, and this is base 2. So notice that base 1 is actually the height of the function at the left side of the interval. In other words, it is the value of the function at the left side of the interval. So what is the value of the function at 0? Remember, the function is 1 plus cosine x. So this would be 1 plus cosine 0. Cosine of 0 is 1 because it's the x value here. So this would be 1 plus 1, which is 2. So that is B1. B2 is going to be the value of the function on the right side of the interval. So in this case, that's the value of the function at pi over 2. In other words, we're talking about 1 plus cosine of pi over 2. Well, cosine of pi over 2 is 0 because that's the x value. So this will be 1 plus 0, which is 1. All right, what about pi over 2? Well, we just did pi over 2, so that's going to be 1. What about pi? B2 is going to be the value of the function at pi. Well, pi is right here, where cosine is going to be -1. So that's going to give us 1 plus -1, which is 0. So B2 is going to be 0. And we just did pi, so we know that's going to be 0 again. What about 3 pi over 2? Okay, remember we're doing 1 plus the cosine of 3 pi over 2. The cosine of 3 pi over 2 is 0. It's that x value again. So 1 plus 0 is 1. So B2 is going to be 1. For the last interval, we already evaluated at 3 pi over 2. So we know this is going to be 1. And now we're back to 2 pi, which is back to this position, which is the same as 0. So this is going to be 2 again. All right, and again, it's because we're doing 1 plus cosine, and at 2 pi, cosine is 1. So this is 1 plus 1, and that's why it's 2. So now we have B1 and B2 for every trapezoid. What about the width? Well, this is going to be the same as the previous problem. From 0 to 2 pi, the width is going to be pi over 2. And each interval is the same width, so it's going to wind up being pi over 2 every time. Now we're ready to write the Riemann sum by calculating the area of each trapezoid. Remember that the area of a trapezoid is 1/2 base 1 plus base 2 times the width. So see if you can trace where I'm getting this from. 1/2 base 1 plus base 2. For the first interval, base 1 and base 2, that's 2 and 1. And of course the width will always be pi over 2. So that's the area of the first trapezoid. And then the second trapezoid, 1/2 base 1 plus base 2. So 1 plus 0 times that width of pi over 2. Third trapezoid, 1/2 base 1 plus base 2. So 0 plus 1 times the width of pi over 2. And then the fourth trapezoid. 1/2 base 1 plus base 2. So that's 1 plus 2 times the width, which is pi over 2. I accidentally put pi over 4 right here. It's really a pi over 2. Anyway, all of this red is an acceptable answer for the Riemann sum using the trapezoidal sum approximation method. However, most people would probably go ahead and simplify this part of each product. So the 2 plus 1 is 3, divided by 2 is 3 over 2, and so on. So there's your Riemann sum.